Please like, subscribe, and share. Stay tuned for more.
Welcome to New Life Academy.
Today we are going to be looking at polynomials. What are polynomials? These are functions that have their variables raised to degree n. It could be raised to degree 2, degree 4, degree 6, 7, 8. Yeah, so to solve polynomials, there are two principles that we must have in mind, two theorems that we must have in mind. That's the factor theorem and the remainder theorem. Now you must know that polynomials can be added, they can be subtracted, and they can be divided. You just have to take note of the degree of the variable and make sure that the variables are the same. Now the factor theorem and the remainder theorem will help us to deal wisely with polynomials. Now there are just some few things that I'll define in order to explain the factor theorem and the remainder theorem. Now f of x represents the polynomial itself. Yeah, so it could be a polynomial of degree 3, degree 4, degree 5. We'll call it f of x or p of x or q of, or g of x, all of that. That's the main polynomial. Now the divisor is what we divide the polynomial by. A simple example: 10x squared divided by 2x. This is the polynomial and this is the divisor. This is the polynomial and this is the divisor. Are we together? So this will give us 5x, exactly 5x. Now, this 5x is what we call the quotient. It's what we call the quotient. And because 2x is a factor of this polynomial, our remainder is 0. Because 2x, because our divisor is a factor of the polynomial, the remainder is 0. If we have something like maybe 3, yeah, anything that is not a factor of the polynomial, then we'll have a remainder. I want you to understand that when dealing with polynomials, there's a factor theorem and there's a remainder theorem. Now the factor theorem says that when you divide a polynomial by its factor, there is no remainder. You have just your quotient, and most of the times it will be written as q of x. But when you divide your factor, your polynomial, by a divisor that is not a factor, then you have the remainder. So that's the factor theorem and the remainder theorem. So I'm going to look at a question right now to enable us understand how the factor theorem and the remainder theorem are used in solving questions in polynomials. So quickly we are going to look at this question. A polynomial p of x equals x minus 1 into x minus 2 q of x plus ax plus b. Now the question says that when p of x is divided by x minus 1, it leaves a remainder of 2. When p of x is divided by x minus 2, it leaves a remainder of 3. And when p of x is divided by x minus 1 into x minus 2, it leaves a remainder of ax plus b. And in the first question, we are asked to find a and b. So for us to find a and b, what do we do? P of x divided by x minus 1 gives us 2. To tell us that x minus 1 is not a remainder, x minus 2 is not a factor, because they both gives us remainders. But nevertheless, it also gives us, it tells us something. It tells us that P of 1, that's from here, P of 1 will be equal to 2. and that P of 2 will be equal to 3. So let's do P of 1. P of 1 means that wherever we find x in our polynomial, we replace it with 1. So that will give us 1 minus 1 into 1 minus 2 into Q of 1 plus A into 1 plus B. 1 minus 1 is 0, means that all of this boils down to 0. But we know that P of 1 is equal to 2, indicating that what's left? A plus B. A plus B is equal to 2. That's equation 1. Now, P of 2, substituting 2 here, wherever we find x, will give us 2 minus 1 into 2 minus 2 into Q of 2 plus A into 2 plus B. Now, all of this will boil down to 0 because 2 minus 2 gives us 0. But then we'll be left with 2A plus B. And then P of 2 is equal to 3. So 2A plus B is equal to 3. That's equation 2. We'll make A the subject in equation 1. We'll have that from equation 1, A is equal to 2 minus B. So we substitute this in equation 2. We'll have that 2 into 2 minus B plus B is equal to 3. So 4 minus 2B plus B is equal to 3. Negative B is equal to negative 1, implying that B is equal to 1. Now if B is equal to 1, substituting B here, it tells us what implies that A is equal to 2 minus 1. So A is equal to 1 and B is equal to 1. I've done the first part of our equation, and we've used the aspect of factor theorem and the remainder theorem. In the next part of this question, we are asked to obtain P of x and also to show that P of x has no other real roots. Now remember, P of x is equal to x minus 1 into x minus 2, Q of x plus ax plus b. Now, this is the divisor, as we saw earlier. This is the quotient, and this is the remainder. So this is the dividend of the polynomial. This is the divisor. This is the quotient, and this is the remainder. So we have already gotten the values of A and B, and for us to obtain P of x fully, we need the quotient. Now, if we have a polynomial, we are told in the question that the polynomial is a cubic polynomial with coefficient of x cubed equal to unity, that's equal to 1. So it's a polynomial in x cubed with degree 3. And if we have a polynomial of degree 3, we have a divisor of degree 2, then the quotient should be a linear polynomial, so of degree 1. So we have that the polynomial is a polynomial of degree 3. If the divisor is quadratic, that's of degree 2, then this must be of degree 1, so that we should have a cubic polynomial. This is already a quadratic. This quotient must be of degree 1, must be a polynomial of degree 1 or a linear equation to enable us have a polynomial of degree 3. Because what we substitute here as Q of x would multiply all of this. And if it has a degree higher than 1, then we are not going to have a polynomial of degree 3. So with that understanding, we're going to assume that P of X is equal to X plus C. That's a linear something. So we substitute that in our polynomial to obtain P of X. So we have that P of X is equal to X minus 1 into X minus 2 into X plus C plus AX plus B. Remember, we already found the value for A and B, so we can just substitute it right away. A was 1 and B was 1, so we can just have plus X plus 1. That's where we are. So the only unknown we have here is C, and we have this unknown C. Now we'll be able to obtain P of X. That's the first question that we're being asked. We have an information that could help us. They say -1 is a root of P of X. When I say -1 is a root of P of X, what does it mean? It means that if P of X it means that P of -1 is equal to 0. And it also means that X plus 1 is a factor of P of X. You see that? If they say -1 is a root of P of X, it means two things. It means that X plus 1 is a factor of P of X. And it also means that P into -1 is equal to 0. So this information will help us obtain C. Let's solve P of -1 equals 0. P of -1 is substituting -1 wherever we have X. That will give us -1 minus 1 into -1 minus 2 into -1 plus C plus -1 plus 1. -2, -3, -1 plus C, and this will give us 0. Is equal to, it's equal to 0, right? Because P of -1 is equal to 0. So this is P of -1. This is P of -1 equal to 0. Now -6 into -1 plus C is equal to 0. Six minus 6C is equal to 0, implying that C is equal to 1. So if we have a value of C equal 1, then we have P of X. What's P of X? P of X is X minus 1 into X minus 2 into our Q of X is X plus C, and C is 1, so I have X plus 1. X plus 1 plus AX plus B. A is 1, B is 1, so that's plus X plus 1. So our polynomial is X minus 1 into X minus 2 into X plus 1 plus X plus 1. So we have obtained P of X. Right now we're going to go ahead and prove that P of X has no other real root. P of X has no other real root. For us to confirm this answer, by the way, the question says that P of X is a polynomial of degree 3 and the coefficient of X cubed is unity. If you open up this, you realize that you have X cubed with a coefficient of 1. Okay, let's go ahead and look at the B part of our question. In the next part of our question, we are asked to show that P of X has no other real root. Now, what do we do at this level? Let's get P of X. This and this gives us x squared minus 2x minus x minus plus 2 into x plus 1 plus x plus 1. So this is x squared minus 2 minus 3x plus 2 into x plus 1 plus x plus 1. Multiplying this will give us x cubed plus x squared minus 3x squared minus 3x plus 2x plus 2 plus x plus 1. That is going to give us x cubed minus 2x squared minus x plus 2 plus x plus 1. So this and this will cancel out. We're going to have x cubed minus 2x squared plus 3. So this is what P of X is. P of X is equal to x cubed minus 2x squared plus 3. Now they're asking us to show that it has no other real root. No other real root. So it certainly has just one real root and no other real root. So how do we get the root of a polynomial? It's by dividing that polynomial by its factor. So when they say -1 is a root of P of X, it means that P of X has a root or has a real root which is x plus 1. It's from here that we get P of -1 equals 0. Are we together? So we're going to use x plus 1, knowing that it's a root of the polynomial. We're going to use it to divide. So right now, let's divide. So this P of X, x cubed minus 2x squared plus 3 are dividing x plus 1. Okay. This divides this will give us x squared. This times this, x cubed plus x squared. Subtracting gives us that. Now I've inserted 0x because there's nothing here in x to the power 1. So I've included 0x. It means nothing. Yeah. So the next number we divide is 3x squared, negative 3x squared. Divide x to give us negative 3x. Multiplying that gives x squared minus 0x minus negative 3x gives us what? 3x plus this 3 will be plus 3x plus 3, and that is it. No remainder. So prove further that x plus 1 is a factor of the polynomial. So this is the solution we have. These are the roots that we have. The roots of P of X, they are x plus 1 and this quadratic, x squared minus 3x plus 3. So this is the first real root that it has. Yeah, x plus 1, it's a real root. Because x equal, if we take x plus 1 equal to 0, x will be equal to -1, and it's a real number. Yes, so we are now going to check whether the roots of this equation are real. So that we can show, or so that we can prove that p of x has no other real root apart from x plus 1. So how do we check this? We know that b squared minus 4ac is less than 0 for imaginary or complex roots. It's greater than 0 for real roots. So let's verify b squared minus 4ac here. Will it be greater than 0 or less than 0? B is -3, so b squared will be -3 all squared minus 4ac minus 4, a is 1, c is 3. This will give us 9 minus 12 is equal to -3. -3 is less than 0. What does that tell us? It tells us that b squared minus 4ac is less than 0. Therefore, roots are imaginary or complex, not real. The roots are not real. So that's how we prove that p of x has no other real root. We divide, we get our solution set of the polynomial. The real root here is x plus 1, as we saw earlier. We go ahead to check if x squared minus 3x plus 3 will give us real root. And we'll check that by using the determinant b squared minus 4ac. If b squared minus 4ac is equal to 0, the roots are equal. If b squared minus 4ac is less than 0, the roots are imaginary. And if b squared minus 4ac is greater than 0, the roots are real and distinct. So we verify it and we realize that b squared minus 4ac is less than 0. And therefore the roots are imaginary. P of x has only one real root. Stay tuned to New Life Academy.